Welcome, everybody. Welcome to class. And I want to see if the hand raising feature works. Cody, would you raise your hand so I can see if it works? All right, hand raising feature works. Excellent. And you can lower your hand if you want. Perfect. So I'm going to do the lecture just like normal, but obviously we're on Zoom today. If you have any questions, raise your hand and I will call on you. All right, where we were last time is talked about how in the old days, the tobacco companies were able to use statistics to prove something that sounds unfathomable. They could create a study where they showed that smoking cigarettes was healthy for you. How could this be done? Well, let's pretend that cigarettes are bad for you. I believe they are bad for you. And let's pretend that the p-value was 0.01. That means that if you run 100 tests, one of them will show the opposite result. So wouldn't this violate some scientific ethic? Like if you go to a scientist and tell them, well, I want you to run 100 studies, they're going to complain when you only publish the one that proves that cigarettes are good for you, whereas the 99 may prove that cigarettes are bad for you. And they would get upset and they would complain, and rightly so. But that's not how this is done. Typically, there would be 100 different scientists who would all be contracted to do a study. And you're under no obligation to publish any study you do. So what if they just didn't publish 99 of them and they only publish one of them? That's one way that statistics can be used to trick people. I don't have proof that this study actually happened, but this is something that you should be aware of that is possible to do. There's a way to totally lie with statistics, and it's by being very careful about which truths you put out there. All right. Now, this course has a lot of information about statistics, and they're not going into it deep. So it's a very, in my opinion, they're throwing a lot of concepts at you without giving you the deep mathematical foundation under it. So we don't have time to go into deep. So try to understand what the different words mean and how to apply them. Like for instance, when we're talking about the Z distribution, and we have this example that we looked at before, and then you go to a Z distribution table to figure out your p-values and what percentage or what area under the curve is here. Just try to become somewhat facile with these concepts, but you're not going to truly understand it, and that's okay. And you really should, in your free time, go on deep dives or rabbit holes, as they say, down YouTube and Wikipedia, to really try to understand these things. And even after you do, you will probably have to do it again the next year and the next year. These concepts are not intuitive. If you feel like they're hard to understand, you are not alone. They're hard for everybody. They're not intuitive, but they're important because the human intuition does not exactly match truth. Eric.
Yeah, someone just sent a message to Discord saying they're in the waiting room.
Oh, thank you. I have to stop sharing to let them in. And now they're all in. And thank you, Eric, and please keep monitoring that.
Yes, sir.
All right. So there's been some interesting research done into, can dogs detect cancer? It's fascinating. Dogs have some of the best olfactory systems, smelling systems in nature. And when someone has cancer, there are certain proteins given off that come out in their breath or maybe even in their sweat. I don't know. And the theory is that dogs are so sensitive that they could detect something before it shows up on a medical test, which is pretty amazing. But let's pretend that we have some data. And the way the data was created was they did a series of tests. In fact, they did 37 tests. And that 37 becomes the denominator in this ratio over on the left, in that fraction there. So they did 37 tests. And in each test, they took face masks that people were wearing. They'd worn them for a certain amount of time. And out of the 4 people that they took the face masks from, 1 of them had cancer and 3 did not. And then they trained a dog to supposedly, not that the dog knows what cancer is, but through a typical animal training regime with treats and whatnot, they tried to train a dog to recognize the one mask by smell when they played them out on the floor, recognize the one mask that was worn by a cancer patient. Now, they did these tests. Now, can anyone tell me if the dog is guessing at random, what will be the probability they get the right answer? Go ahead, Miles.
0.25.
That's right. So that's why we see on the bottom here, you have 0.25 would be the mean. That would be what you would expect. That's the mean. So our null hypothesis is that there's nothing special in what the dog's doing. The dog is just guessing, right? And the true probability is going to be 0.25. The alternative hypothesis is that, is that the dog is actually making a correct guess more often than can be described by chance or explained by chance. And the dog ended up guessing right 29 times out of 37, which is not perfect. Any question? Heard something? No? Okay. So 29 times it got it right. So that means we have a 0.78 as the proportion we got correct. And you can see that 0.78 is way outside that curve there. So now we take that 0.78 and we are going to estimate something called a margin of error. Now the margin of error begins with us making a decision. This is not coming from the data. This is just a decision that we make. We decide, I want to be 95% confident. And that is the number that we choose as a person who has to do something with this data. If you are the FDA, for instance, and you want to determine if dogs should be used in an actual medical test, well, you would have to decide what confidence interval are you comfortable with, and there's probably legal implications. But that 95 just comes out of someone's head. They're just deciding, I want to be 95% confident. Then we can use the Z-table to give us something called the confidence level multiplier. And it's literally just the Z-score that we saw before. So in the same way we went here and we had some number, it was like 0.33 or something. It was, in this case, instead of 0.33, our number is 0.78. This 0.78, if we go to that z-score table, whatever, we get some other number. The number turns out to be, 1.96. That is our confidence multiplier, the confidence level multiplier. Now, not every set of data has the same sampling distribution. So we look at the samples that we took and we compute the standard deviation of it. And that is 0.068. It's very small. That's why this curve is so tight here. And 0.78 normally doesn't seem like a very outlier number, but in this case it is. And so we end up with 0.78 plus or minus the margin of error. That is literally all a margin of error is. You get your sampling distribution, you multiply the confidence level multiplier, and you get 0.78 plus or minus 0.133. That means this value right here, you got a 0.78 because you got 29 right out of 37. What you don't know is how sure are you that you'll always get some result like that. If you run the whole test again, maybe next time you get 25 out of 37 or 33 out of 37. So what you decide is, I want to be 95% confident. Remember the 95% confident interval. So that means that 95% of the time you will be in the range of 0.78 plus or minus 0.133. This is how we put bounds around things, because in statistics, you can never be totally sure. The idea is not to be totally sure. The idea is to give an idea of where things probably are. And you can say with certain confidence that something is in here or isn't. That's the idea. Any questions before I move on? All right. Now, every time you come across a statistical question, these are all from ZBooks, a lot of these are, there will always be some number that it all comes down to. And this one happens to be the proportion of all homes in the Northwest Iowa with radon levels above action level. And that just means dangerous radon levels, I guess. And 0.716, that's really high. 70% of homes in Northwest Iowa have high radon levels. I don't know, that doesn't sound healthy to me, guys, but let's hope it's just theory and not real data. Well, let's look at the things in this picture and make sure we understand everything. You always have to have a null hypothesis, H0 or H null. And the null hypothesis is that the homes, the real value is 0.716. And the alternative hypothesis is that it's higher than that. And what you'll see is that we take some samples, we take some observations, and that's what we have done here. They went to a bunch of homes, 351 homes to be exact. And turns out 285 of them had this thing we're looking for, which just happens to be radon level above high action level. There's so many extra words they just threw in here. Try to ignore the fact that it's radon levels above action level. It's just a thing we're measuring. 285 had it out of the 351 that we went to. And that gives us a number 0.812. What we want to know is that something to be worried about? Are we just within the confidence level or just in the near midst of the norm? Or are we far away enough from the norm that we can reject the null hypothesis? The null hypothesis being that the value, the true value, if you measured everybody and got perfect data, the true value would be 0.716. So then we go over to the test statistic box here, and we get our Z statistic just like usual. Now there's this notation here that Z is curly line normal 0, 1. All that curly line means is distributed according to. So every one of these curves, like the one at the bottom right, every one of those curves is a distribution, as we discussed. A distribution is just a curve. Now, every probability distribution has one thing in common, where if you integrate it under the curve, it would add up to 1. It would integrate up to 1. The probability across the entire thing is 1. Now, normal distributions are a specific type of curve that look just like the one at the bottom right, and they can be fully described by two numbers, the mean and the variance. So when you say normal 0, 1, that means a normal distribution with 0 mean and unit variance, or a variance of 1. And if the variance is 1, then the standard deviation is also 1. It's just a very nice, easy mathematical object to do things with. Now this one, our data that we took, which they allude to in the bottom left, the data that we received is not a 0, 1 normal distribution. It has a mean of 0.716 and a variance of 0.024. So we have this distribution instead. So we plug those numbers into our Z and we get 4, the number 4. And turns out the number 4, whether it's positive or negative, is way outside that curve. And that gives us a nice, really, really low p-value. And what this tells us is that we can reject the null hypothesis. I encourage you guys all to watch YouTube videos about this again and again, because it's a weird way of thinking. Instead of saying, I want to prove that homes in Northwest Iowa have a 71.6% chance of having a high radon level, you say that's my null hypothesis, and I'm going to reject it with the data. So that's what we've done. We've rejected it. And since our Z level is positive, that means we're above. So we don't say, I've proven that the true number of homes with high radon is higher, but that's in essence what you're doing. When you say, I've rejected the null hypothesis that pi is 0.716 with a positive Z statistic and a p-value of 0.00007. That means you're very confident of this. Remember, a lot of this is hard to understand just because of the weird way of talking. There is a deep mathematical reason behind the weird way of talking, but you just got to expose yourself to it again and again, and it will eventually sink in. The examples in the book, they're okay. They're a little bit difficult to understand. You may have to talk to your TA to help you through some of them, or may have to come to office hours when I'm healthy, that is. But let me know how it goes. Okay, Miles, you have a question?
Yeah, sorry. So this would be a binomial distribution, right, for the data, or is it Bernoulli?
I don't know.
Okay. Do you know how they got that standard deviation, or is it just
From the actual data itself. So they got in, yeah, I don't exactly know how they computed that number.
Right.
There's a lot behind the scenes, supposedly, that they didn't show us. Sorry, couldn't answer more. Okay, now this one has a lot of things that they throw at you to make it confusing. But try to remember that the null hypothesis tries to bring things down to one number. So we have two things here, pi v and pi I. Pi v is the proportion of homes with basements for the population of homes with valid results. And pi I is the proportion of homes with basement for the population of homes with incomplete results. It's a really weird way of posing this, and it's they are overcomplicating it. And I think they're doing that for a reason, maybe so you have to get to the core of what's going on. So if we think about those results we had before with respect to radon levels, some of those homes were homes with basements, and some of the homes didn't have basements. Well, the ones without basements we're not even considering here. Radon seeps up from the ground through holes in your basement. So out of all the homes, just the homes with basements, we can divide those into two classes. Some of them we had valid results, and some of them we had incomplete results. Now the question is, for the ones with valid results, how many of them had what is the ratio of homes with basements to the homes with valid results, and the homes with basements to the ones with incomplete results? I don't know why this is an interesting question. It's not interesting to me, but they put in the book, so let's just try to pick it apart a little bit. There's nothing mysterious about whether or not a home has a basement or not, and there's nothing mysterious about whether a home has the larger number of homes with valid results or not. So let's just imagine those as abstract numbers or sets, and then we compute these ratios that they want. Now the question is, are they the same or are they different? The null hypothesis is that they're the same, or the way you could describe that is pi v minus pi 1 pi I equals 0. And then the alternate hypothesis is that they're not the same. So try to forget all of the details of where the numbers come from and just narrow it down to, I have this thing that's either a 0 or it's not 0. That thing happens to be pi v minus pi I, but it's just, is it 0 or is it not? And once you narrow it down to that, you just go through the normal steps like you would with anything. And you can reject the idea that it's 0 if your Z statistic is high enough. And it turns out we can reject it. And we can reject it with a p-value of 0.001, which means we can reject it with high confidence. Even though this seems like a different situation, it can be treated no different than any other situation. All right, any questions before we go on to something a little bit harder? All right, so all of these assume that we know what the standard deviation is, or a lot of these have assumed that. When we use the Z statistic, normally you compute it with the standard deviation. Now, if you don't know the standard deviation and you have very few examples in your data, your observed data, then you have to do something kind of creative. And we didn't know what to do for a long time until a certain Guinness Brewery employee named William S. Gossett came along. Now, he was working in the brewery and he was I guess you could call him their head statistician. I don't know what his actual title was, but he would run a batch of brewing of Guinness, and the data, the inputs were, things like temperature, how much of this ingredient and that ingredient, how long they cooked it, and certain, outputs would be, taste quality. And he had to know, or had to be able to decide statistically if he had the input settings right. Now, it's not something you can discover and then just keep it that way forever, because there is no way to get exactly the same ingredients every time you do this. Life is messy. And when you grow, oats and barley in the field, and you buy from different farmers, you're going to get a slightly different product every time. And everything is going to process differently depending on the temperature and the humidity levels in the environment, in your plant. So he had to do some fancy statistics to determine this. Now, it would have been fine. He could have used the Z statistic if he had a lot of samples, but he often had to do this with very few samples because every run of the brewing process was very expensive. So he came up with something called the T statistic. Now, the Z statistic, which is what we've been talking about, is based on the data that you get. That's X is not just one value, it's a whole bunch of them, minus the mean divided by the standard deviation. That gives you your Z statistic. Notice that the number of samples is not in here. You can assume that the number of samples was used to determine the standard deviation and the mean, but it in itself, the N, is not in there. So what he did, he realizes that N needs to be in there. And somehow this equation or statistic needs to change. If you have very few N's or a very low N, then you cannot be very sure. The more N you have, or the higher your samples are, the more sure you can get to. So the T statistic is just slightly different. Instead of assuming we know the standard deviation, we use the sample variance here. That's the S. So we have the same thing on the numerator. We're taking all of the values that we had before and we're subtracting out the mean, but then we're dividing by this parenthetical statement, which is the sample variance divided by the square root of the number of samples. And then he wrote this amazing paper that proved that this is a good, valid statistic to use in these situations. Now, the interesting thing is that when you get to an N that's about 30, the square root of 30 being something between 5 and 6, the sample variance divided by that really gets close to the actual standard deviation. And we use 30 as a good rule of thumb to use the Z instead of the T. So you can think about this flow chart. Do you know the population standard deviation? If you do, great. If you don't, use the T-score. But let's say you do know the standard deviation, but your sample size is low. If it's very low, it's below 30, you still want to use the T-score. And you'll need to replace the S and the T-score formula for, okay, that's for, yeah, formula for the standard deviation. If your sample size is above 30, then just use the z-score. It gives you almost the same answers. So just to review again, he needed to do statistics without being able to compute the z-score. That's because his sample size was low. So he invented this t-score and proved in a paper that it would work. Now, the funny thing was, since he was an employee of Guinness, they didn't want him to publish it under his name. So it's not called Gossett's t-score. He just signed it student, as if he's a student somewhere, and is still known to this day as student's t-score. So remember that rubric. If you have more than 30 in your sample size, just use the z-score. Below that, use the t-score. Okay, now in order to do this, he had to introduce this concept called degrees of freedom. And your degrees of freedom, now this may have come out before him, but he uses it here. The degrees of freedom in the system is the number of samples minus 1. And there's deep math behind this that I understood at one point and don't right now. And you're welcome to go in some deep dives. But just remember that the degrees of freedom is the number of samples minus 1. There's a lot of nomenclature here. And you're not expected to understand the statistics, but just try to remember what the words refer to. And then we use things like T tables and Z tables to figure out the answer. And online you can find Z tables and T tables. Now before, when we did the Z table, what we did is we had our Z statistic, which was like 0.183, I think. And then we used that to triangulate and find this section. Can you guys see my mouse?
Yes.
Good. So we used that to triangulate and find this, and this was our p-value, 0.0336. Now that's great, and you will need to understand z-tables. That's good and fine, but t-tables are totally different. So try not to get confused, even though it's very confusing. The way we use a t-table is kind of the opposite. And let's go through this example here. Katerina was testing. She had a null hypothesis, and the null hypothesis was that mu equals 0. And the alternative is just the opposite. Mu is not 0. Now she only has 6 observations. This is very small. So we're going to use the t-test. And she calculated her t-statistic using the math we saw before, and she gets 2.75. Now the question is that meaningful or not? Can we reject mu equals 0 or not? So we're going to find out. Now, this table is kind of the opposite of the other table. Instead of finding our p-value out in the middle here, we're going to find our p-value at the top after going to the middle. So we know that she has 6 observations. So our degrees of freedom is 5. And we start on the left, df. So the degrees of freedom are 5. You go down to the 5, and then you go to the right and look for the value that's closest to that t number you got. We got a 2.75. So we're going to go over to the right to find 2.75, or the closest one we can find is this, 2.757. Then we find the p-value at the top there. So our p-value is 0.02. Obviously, Python can do this better for you than looking up in tables, but this is how it has been done historically. So I wanted to show it to you. This says a p-value of 0.04. Can anyone guess why? The tables are always single tail. So each tail of the distribution is the area to the left or to the right. And the table indicating the numbers for 0.02, that 0.02 is the area under the curve only to one side. But remember, our alternative hypothesis is that mu does not equal 0. It can be higher or lower, it doesn't matter. So we have to double it to get a 0.04 for our p-value. So lower is better. 0.04, it's not bad. We can still reject the null hypothesis, but not with as much confidence as we have in the other examples. All right, that is the end of this section. Does anyone have any questions before we move on to the next section? All right. Next section, we are talking about relational databases. And I think about databases as something that was really exciting and cutting edge technology in like the 1980s. And since then, it's boring. It's there, it's behind the scenes. Everything you do on your laptop, your phone, when you go to the bank, when you do anything and go to like renew your license, it's all supported by many, many databases. This is not sexy technology, but it is trustworthy and stable, and the world depends on these. They're so important, but they're so not sexy these days. People don't talk about them. Now, in contrast, at least until about a year ago, blockchain was very sexy and important, and people were talking about blockchain this and blockchain that. The blockchain, all it really is a distributed database. They use fancy math to make sure that you can't alter the database unless you have permissions. But in essence, it is just a database. So let's get into this. What we have here is a very simple database with two tables. And one of them is called the country table. The other one is called the city table. In the country table, we have some entries, and one for Japan, Italy, and Ecuador. And for the city table, we have a whole bunch of entries. And the one for Osaka just happens to be in Japan. One for Rome just happens to be in Italy. But the word Italy does not appear in that row. What instead we have is the country code. And if we wanted to get the actual full name, Italy, we would have to go up to the country table and extract or ask it, what is the country name for country code ITA? And the same thing for ECU. If we wanted to know the name of the country Quito is in, we would have to read this row from the table city, and we get that country code. Then we make a separate query, or there's a thing called joins, but we can make a separate query about, tell us more about this country code ECU. What is the name? And then this table would give us Ecuador. Now, there are restrictions on what you want in your relational database. These are restrictions that are there to help you maintain a set of data in a way that it's clean and usable and reliable. Restrictions like you don't want any two rows to be exactly the same. So if you have a row that says Japan, JPN Japan 377829 Asia, you want only one of those rows. You don't want to have another row with exactly the same values. Now, also, you definitely don't want two rows that have values that are different on just the surface area. Let's pretend you had two rows. One said Japan had a surface area of this number, and the other row said Japan had a surface area of some other number. That would be terrible. That would be problematic, because then you wouldn't know the truth, or you wouldn't know even what you think the truth is. What if you had two different rows and one of them said that Japan was in Europe? As a human, I know that's wrong, but what if you didn't know and you were querying the database to find out? So we need to put guardrails on how things can be structured in a database. Database is meant, first of all, to have performance. Obviously, you could put all your data into a flat file, and every time you want to get an answer, you can read through the entire file until you get to that line. But that is so slow. That is annoying. And in the old days, that is what they literally had to do. But then they came up with the database, which structures things in the computer, on the disk, and in memory in such a way that when you ask for something like, what is the surface area of Japan, or what is the surface area of Ecuador, it doesn't read the whole file. It goes just to that one row that has the information you need, gets exactly what you need, and returns it to you super fast. Databases have been getting better and better at this over the years. But that performance, getting your answer quickly, is the first reason why we developed them. Next thing is security. Let's say we have a massive database with everybody's medical data. And you come to it and you want to ask a question. We need to make sure that you are able to get your question answered. However, we don't want you to be able to ask questions about anybody else's medical data. So there needs to be security rules that, first of all, verify you are who you say you are, and then only let you ask questions that you have permissions for. So every table or even columns or rows can have certain security restrictions. Remember, each one of these is a table. The columns are the vertical things, and the rows are the horizontal. So in this sense, you could say the relational databases can be thought of as rectangular. They are structured according to this kind of way. So security was difficult to add, but they were able to add security without affecting performance too much. But it was another layer of complexity. But we've been at this since maybe the 1970s, so they've gotten pretty good at it. Now, the next thing is concurrency. Databases manages conflicts that occur when concurrent users update the same data. Like, let's say you and your mother were both logged on into a system, and you both noticed that the address was wrong for your account, maybe here at Gonzaga or something. And you made a change and your mother made a change, but you actually made changes that were a tiny bit different. Like maybe one of you put a comma after the name, after the word Spokane, and one of you did not. They just put Spokane space or Washington. So which one does the system use? Well, the manager of the system or the sysadmin will need to decide, maybe I choose the latest one, maybe I don't. But what you never want to happen is that the system just totally breaks and says, I don't know what to do. So when two separate people are editing the exact same field at the same time, databases need to manage those conflicts. And we refer to that class of problems as concurrency. Like so many things we've already talked about in this class, it's sort of a vocab class. You're learning new vocabulary. And these slides are here for you to refer back to. And I really encourage you to refer back to these things. Concurrency is that broad class of problems. How you resolve or manage those conflicts is up to the database admin or administrator. But know that databases are able to do this. And this becomes even more complicated when you have your one database running on multiple computers. But these are all things that we've been working on since the 70s and 80s. So we know what we're doing now, and we have solved these problems really well. Okay, now what if someone's doing a transaction and your database is running on a machine that loses power? What if there's some tsunami or whatever, and you have to reboot everything afterwards? Let's say you get the hard drives and then you need to bring your database back online. And there were a bunch of transactions that began but didn't finish. How do you know what to do? Well, databases are able to restore from scratch or from a consistent state after some kind of failure. And this involves a lot of different things, a lot of different moving parts. And we've mentioned a couple of them before. Hopefully this looks familiar to you. And the way we make sure that we handle a lot of those problem states I mentioned before was to make your database ACID compliant, atomic, consistent, independent, and durable. So atomic means that whenever a transaction starts, either it fully completes and it enters the database for good, or it doesn't. So if you were halfway doing your transaction and the machine lost power, when you turn it back on, that transaction would just be merely dropped and ignored as if it didn't happen. Now, consistent means you only have one answer for any question. Like if you were to ask the database that Gonzaga runs, what is your address? There should only be one answer, and it should be consistent with itself. So let's say that you have two separate tables in the Gonzaga database. One of them is for employee addresses, and one of them is for student addresses. What happens if one of the employees decides to take a course? Now they're also a student. Now you might have their address stored in the employee addresses and the student addresses. There is an opportunity for it to become inconsistent. So a well-defined database doesn't have this problem. Instead of having two different tables, there's just one address table. That's one way to make sure it's consistent. Independent means that if you have two different people both doing a transaction, the process that's handling the transaction for the first person doesn't even have to think about that second person. All it needs to think about is what's happening right now in its interaction with that one person. It can happen independently of anything else. And the final thing, durable, is what do you do when the system goes down, loses power, the computer breaks, whatever? You need to be able to rebuild the entire database using what's on disk and have it be durable. The other set of problem states we talked about before regarding databases is known as the CAP theorem: consistency, availability, and partitioning. And this example, what we talked about, if you remember, I drew on the board a network of ATM machines, so bank tellers. So let's pretend you have a network of bank machines that do not have any partitioning, meaning they can all connect to each other perfectly. Then you have no problems. You can make sure they're on all the time, which means they're always available. and you can make sure they're always consistent, which means the numbers always match up. However, if you have partitioning, that's where the problems start. Let's pretend that the network goes down, the internet, not the electricity, just the network for a given machine. And then you come and you happen to try to take money out of your account at that machine. That machine has been separated from the network, and this is a partition. When you put in your card and you ask it, how much money do I have in my account? It doesn't know the truth. It only knows how much money you had in your account the last time it was connected to the network. So when you ask it to take out money from your account, you might actually have zero in your account. Maybe you went to another machine that was connected, took out all your money. Then you come to this machine and it says you still have $1,000 in there. So you take out another 1,000 and you're tricking the system into giving you $1,000 that you don't actually have. So how does the bank deal with this? Sometimes they just trust you based on your credit rating. Other times they tell you, no, you can't do that right now. They will say that withdrawal is not available. That means you lose out on availability. Now, the CAP theorem is what's known as a trilemma. It's like a dilemma, but with three things. And this means you can't have all three at the same time. If you want to be available all the time, that means you're going to lose on consistency. If you want to be always consistent, you're going to lose somewhere else. So these are some of the terminology you'll need to know to understand databases and how they work. We'll keep going here. In every table, you should have a unique identifier or a primary key. You aren't forced to, but you should. It's a good practice. When you think of countries in the world, you would assume as a human, if I were creating this database, that a country code only refers to one country. You can't have a country code that refers to 2 or 3, because then you wouldn't know which country your code was referring to. And the whole purpose of having a country code is to make it very clear which country you're talking about. As a human, you know that, but computers don't make assumptions like that. So you have to tell it. And when you make the country table, you're going to want to tell it that the primary key is the country code. And you can even have more than one primary key. You can have country name be a secondary unique identifier. They can both be primary keys or unique identifiers. They're just things that make that line unique. Now, there are different kinds of databases. There's MySQL, there's Postgres, there's a bunch of them. And going back to the 80s, there's been many more that we don't use anymore. They all share some similarities. So just try to understand the theory behind this. And when you actually have to use databases, you will want to look up the queries that match the exact database that you're using. As an example, this is a terminal I've opened to a MySQL database. Now, the command show databases is very obvious what it does, right? It shows which databases that I have running on this database server. And there's even one called MySQL, and that just does, I think, some of the back office stuff for MySQL. I don't actually use it. So we're going to use one of these databases. So when I do the use command, that means the next query I make will be specific to that one database. Now remember, every database can have multiple tables. So I want to see what those tables are. SQL is the language I'm making these questions in. And it's a query language that you use to ask questions of your database. That's all it is. And it's a simple language, but there's a lot of interesting complexities, and people are able to write SQL queries that are very hard to understand. But I suggest you stick to the more simple queries, and I'll show you where you can see some samples in a minute. So this show tables command, we write it like that. It always ends in a semicolon. SQL always ends every command with a semicolon. And it turns out these are all the tables in that database. Now, let's look at one of those tables, and let's look at the crimes table. This is actual crime data from an open source database that you can download. And I've put it into this MySQL database. So select star, that's a wild card. That means any of the columns from the table called crimes, and we're going to limit 100. That means we don't want to see the whole thing. In fact, let's just limit it to 10. Okay, so this means get that data. That's what the select command does. If we wanted to look at just one or two columns, then we could look at just the lat long. And then we get just the lat and long. Now there's another way to filter these. What if we want only a certain kind of crime type? This C-type column tells us what kind of crime it was. So let's look at just the ones where the crime type was assault with a dangerous weapon. Let's just get 20 of them. So here we go. Here is the lat and longitude and the dates of these assault with dangerous weapon. And it even tells you sometimes what weapon it was in the method column. And this is how you get to the answer you want. And some people like to write SQL queries that are so complicated they take up the whole page. I suggest you don't do that, but rather use a simple query to get the result into your Python code, and then you do the more complex manipulations in your Python code. There is no right answer. That's just my suggestion. So as we see here, each of these tables has its own primary key. Back over here, the primary key is just an ID number. Now, this ID number was generated when we created the database. It is not special in any way. So it's kind of unreliable. If I were to create the database all over again using the same data, if I happened to process the input data in a different order, I would probably get a different one of these, a different ID number for each crime. Now, there is no real dependable way to say that a given crime event needs to have ID number 45 or 48. So I'm not sweating it too much. But when you think about countries, there is a real third party or out there in the world reason why Japan should have JPN as its country code, because it's similar to the word Japan. And ITA comes from the word Italy. And these country codes were chosen by humans to be a dependable way to refer to that concept known as Japan, Italy, or Ecuador. That's why they really serve us well, is using that as the unique identifier or primary key. And the same thing with these city names. Now, where this might break down is, what if you said, I want to send you to the city of Springfield in the United States. Who knows why that would be a big problem? Why would it be a big problem if I told you you need to go to Springfield, United States? Nicholas.
There's multiple different cities named Springfields in the country.
Yes, in fact, I think it's the only town name that there's one of those in every state. I think in all 50 states. I'm not sure about that, but that's what I heard. Maybe it's only the lower 48. But that means that if you're talking about just cities, you could no longer use Springfield as your unique identifier. For a city like Boston, probably could, but there might be a Boston somewhere in Idaho or somewhere. So you have to do the city name and the states. And those two together can act as a unique identifier. So sometimes you just need one column, sometimes you need multiple columns. Okay, now this is a country language table. You get a country code in one column, the language in the next column, and is official in the next column, and then maybe percentage of speakers. Every horizontal thing here is called a row, of course, and the vertical ones are columns, and a cell is just one of these values. There can only be one thing in the cell. That one thing may be something complex, like a list. I believe that MySQL does not support lists. I think Postgres might. But depending on the database you're using, you can put something complex in that cell or not. But the cell always has one value. And a database is merely an efficient, secure software package that will get you the answer you want quickly. And that answer, there better be only one of them. And that's what this is. Now, here's the challenge. What if we were to put South Africa on this table? South Africa has 11 official languages: English, Afrikaans, Zulu, Xhosa, and a bunch of others. So you would end up having some country code for South Africa, and you would have 11 of those rows where the is official is T. And you may have even more rows where the is official column reads as an F. So in that case, the only way to say that you have a unique row is by using all three of country code, language, and official. Use all three of those as your unique identifier. You cannot rely on just one column or even two. Now, percentage is a floating point, and it's very bad form to use a floating point as your unique identifier. You never want to do that. And most databases will not even allow you to do that. Just remember that. Unique identifiers are typically strings and integers. All right. This is a table that has a problem. So the problem is not super clear, but basically they're saying that someone tried to enter two different values into a country name, Italia and Italy. This is not the best way to do it. Both those names are true, depending on what language you speak. What's a better way to do it is to have some column that says country name in English and another column that says country name in that country. Or you could have different columns for the way different countries say your name. there are countries like Estados Unidos, United States, that depending on where you are, you say it differently. Like in Russia, they say Shah. In Germany, they don't call themselves Germany. They call themselves Deutschland. In Italy, they don't call them Deutschland. They call the Germans Tedeschi. In France, they don't call Germans any of those names. They call them Allemand. So and in Russia, they call them something totally different, Nemetsky. There's so many complicated ways that this can go wrong. And when you enter things into a database, it's important to be cognizant of those and put things into a way that when you need to ask your question, you will get the right answer and only the right answer. Here's another table that has an error. I want someone to raise their hand when they see the error. Miles.
There are two identical rows.
That's right. There are two identical rows. And this never happens in the database. The way the database makes sure it doesn't happen is because when you try to put in that second identical row, it will either merely update the one that's already there, do nothing to it, or it'll give you an error, reject your insert. Insert is how you put something in a database, or it will do something else. It will never let that happen. Okay. Look at this for a second. Is there something wrong here? Actually, Miles?
There are two columns with the same name.
That's right. There's two columns of the same name, just the word name. And obviously Japan, JPN, if you ask for what is the name column from the code JPN, it would have two answers, and databases don't allow this. So if you wanted to create a second column, also called NAME, it would give you an error and it would break somehow and tell you can't do it. If it lets you do that somehow, then you know something's really wrong. Maybe you have an extra space in there that you can't see. I don't know, but be careful not to do that. Okay, now there's nothing wrong with this one, but it brings up the concept of nulls. A null is when you don't have anything in that column. You can tell your database, I don't allow nulls in a certain column, or you can tell it it's fine. In this one, it seems to be fine to have either the surface area or the capital name be null. And a null is just, it's just not there. We just don't know. And I'm gonna talk for a minute about this, but we won't do any more slides today. A null is not the same as zero. There are times that zero is a meaningful value, or even the empty string is a meaningful value. And you need to know that, and you need to differentiate that from the situation where you just don't have the data. That's why null is important. Null, also in Python, we write it as none with a capital N. And depending which database format you're actually using, MySQL, Postgres, whatever, they could treat nulls a little bit differently. And different languages treat nulls a little bit differently. So it's going to differ in every circumstance, but I want you to understand that the reason we have nulls at all is because we need to differentiate the case where your value is zero or the empty string, and when you just don't have data. Those are two different situations. Any last question before we stop for the day? All right. Thank you, everyone. And I hope to see you in class physically on Thursday. But if I'm not better, then we'll do another Zoom and I will tell you on Discord. Thank you, everybody.
Thank you.
Thank you.
Thank you, bye.
Professor,
Thank you.
Yeah.
sorry,
Okay.
when that first deadline for the semester long project, when was that we had to like have some analysis of the
7th.
data? March 7th. Okay.
I think it's March 7th. Yeah, that's right.
Yeah, I've been talking to one of my friends who does a lot of natural language processing stuff. And he's been helping me with setting up some stuff to kind of improve the space. I was also, I wanted to let you know, I'm also I'm gonna be gone from this Saturday until this Wednesday. I'll be traveling with the Bulldog Band for the WCC tournament. So I just wanted to let you know in advance that I'll be
What do you
gone.
play?
I play the mellophone. It's in
Mellophone. I don't even know what that is.
Yeah, it's in the trumpet family. It's what they give to French horn players. Because it's in the same key. It's just kind of larger, and so it's a little lower in pitch.
Awesome. Do you also play the French horn?
I do play the French horn.
There are so few of those in the world. If you get really good at it, that's job security for you, I hear.
Yeah. I will see you hopefully Thursday.
Excellent.
Professor, I had a question about our next check-in on the final project. We've cleaned up our data and made like a couple models of averages. But were you wanting more of models pertaining to like a conclusion? Or
We don't have to do that now, but anything you can show me is good. If you can, I want to see it if I can. If you can use Matplotlib or something like that to make diagrams, one or multiple, whatever you want. And if it makes sense, if you see some kind of curve or a line, you can use linear regression or curve fit.
yeah, I just did a line of best fit, but now that was before our last lesson, so I was planning on switching that to the curve fit. And then I totally forgot. I didn't realize that we were on the Zoom today, so I hopped on late. So sorry about that.
Okay.
But
Okay.
yeah, that's it.
Okay. Thank you.
Yep. I'll see you in class. Have a good one.
Joy, do you have a question?